if we were to power all the cars from biofuels, and if you grew the biofuel on the verge of the road, on the side of the road, the strip alongside the road, how wide would that strip need to be to provide enough biofuel for all the cars? So we can make a rough, approximate, inaccurate guess by saying vehicles are going at 60 miles per hour. Let's just have one lane of these vehicles. Assume they're doing 25 miles per gallon. Biofuel productivity is 1,200 litres of biofuel per hectare per year. That's a typical figure for European biofuel plantations. And finally, an 80-metre spacing between the cars. So all of these are rough, arbitrary numbers. You take the top number, you divide by the other three. You're careful to keep track of the units, and you find that the strip needs to be 8 kilometres wide. I'm going to describe energy consumption and what energy we could produce from various sources using personal units. I think as soon as you talk about numbers that come in thousands, millions, billions, or trillions, then most people don't understand the difference. They are actually different, but those are quantities that people aren't very good with in their heads. So I'm going to use units where personal numbers come out in 5s, 10s, and 20s, because those are numbers that people can compare and be familiar with. I therefore measure energies in kilowatt hours, because everyday choices that people make come in small numbers of kilowatt hours. Your electricity meter at home and your utility bills probably come in kilowatt hours as well. And simple choices that you make involve small numbers of them. For example, if you illuminate one 40-watt bulb for 24 hours, that uses 1 kilowatt hour, and it costs you 10 cents or 15 cents. If you eat food, the chemical energy in the food that you eat amounts to about 3 kilowatt hours per day. If you take one hot bath, that's 5 kilowatt hours of energy to make the heat in the bath. If you take a litre of petrol and set fire to it, that dissipates 10 kilowatt hours. And if you have a Coke habit and you drink the Coke and throw away the can, the embodied energy, the energy required to make the aluminium in the can that you threw away, is about 2/3 of a kilowatt hour. So stuff also comes in small numbers of kilowatt hours. I'm going to measure how fast we use energy, which we call powers. When I say power, I mean any form of energy consumption or production, not just electricity. I'll measure powers in kilowatt hours per day. And physicists and engineers in the audience might spit and say, why don't you just use watts or kilowatts? But I like this unit because it's clear that it's a rate of doing something, because it's got a per day in the name. And the answers will come out in 5s, 10s, and 20s, which is a good size of unit. There are some choices we make that come in larger, slightly larger numbers. For example, if you drive an average European vehicle 100 kilometers, then you use 80 kilowatt hours of energy. If you fly from London to Los Angeles and back, then that one decision involves 10,000 kilowatt hours of energy expenditure for a single passenger. Most people don't do this every day, however, and if we say on average, if you do this once a year, then how much energy are you using per day thanks to the yearly intercontinental travel? Then the answer comes back into the 10s, 20s, 30s. We're talking 26 kilowatt hours per day for one international trip per year. Similarly, heating a typical North American house in a bit of North America like Ottawa uses 80 kilowatt hours per day. I don't know what a California figure would be, but maybe if you have a lot of air conditioning on the go, it might be a similar sort of figure for a 3-bedroom house. Other things get onto the list of things that we're urged to do something about when we want to save the planet or save money. The London Mayor ran an information campaign with saving the planet as the theme, planet repairs, and there were 7 things that were recommended. And one of the 7 things on the list was that everyone should unplug their cell phone chargers when not using them. If every London household unplugged their mobile phone chargers when not in use, we could save 31,000 tons of CO2 and millions of pounds per year. So clearly this is very important. It comes in millions and thousands of things. So let's just check the numbers to confirm that these black planet-destroying objects, that's a cell phone charger, they're about as evil as Darth Vader. So here's the number for a phone charger. In watts, it uses about half a watt when you leave it plugged in. And so the energy saved by switching it off for a whole day, which is 86,000 seconds, is exactly the same as the energy used by driving an average car for 1 second. Both of those are equal to 0.01 kilowatt hours. So the energy conservation feat of unplugging the cell phone charger is in the 0.01 kilowatt hours ballpark. Now, should this be in our top 7 things that we recommend to children as things they should do so that they've done their bit and saved the planet? I think it doesn't belong in the top 7. I suspect there are other things that should be higher in the list. So, let's talk about actual total consumption using these units. In a country like Britain, a typical European country, average power consumption is 125 kilowatt hours per day per person. I emphasize this is not just electricity, this is all forms of energy. You take the total coal, gas, oil, nuclear, and everything, hydro, and share it between 60 million people, and you get 125 light bulbs per person. Another way of thinking about 1 kilowatt hour per day, by the way, is not just the same as one light bulb, it's also the average power you could extract from one human servant. So it's as if every European has got, in this high-tech age, 125 quiet techno servants doing stuff for them. The average American energy consumption is 250 light bulbs per person, 250 kilowatt hours per day of energy in all forms. Where is this going? Well, in Britain, it's going into roughly transport, heating, mainly hot air, and other stuff, much of it electrical. So a very quick cartoon, which isn't accurate but is good for quick conversations, is to say the energy goes into transport, heating, and electricity, 1/3 each. Now, when we talk about getting off fossil fuels, in Britain we get 90% of all that energy from fossil fuels. When you talk about getting off fossil fuels, one of the options on the list is renewable power sources. And renewables often involve doing something on an area of land or possibly an area of sea. And so we need to talk about how much power you can get per unit area. The unit in which I'll measure powers per unit area is going to be the SI unit, the watt per square meter. And we need to know about population densities as well, and there's a great variety of population densities. Britain's population density is 250 people per square kilometre. That's the same, incidentally, as Massachusetts, and New Jersey's population density is a little bit bigger. So the messages that we learn for Britain about the scale of renewables required to supply a British standard of living, they apply equally to several other countries and to some US states, in particular Massachusetts and New Jersey. The population density of America is significantly lower than Britain's. It's about 8 times lower, maybe.